In this session, we'll explore a single artificial neuron with a single data vector, and we'll develop a steepest descent algorithm for that. For our artificial neuron, the first thing we do is we need an objective, and the usual way to get an objective is from a residual error. So let's write down the residual error, and here we will be, for the moment, indifferent as to which activation function we'll use, and later in the session we'll pick one activation function. So the residual error is the difference between the label and the results of our computation. And we'll write that as residual, and we'll note, because we use residuals elsewhere in this course, we'll say this is the residual for an activation function of an augmented weight vector, and we'll define that as being the difference between a label and the activation function, which is it has an argument which is the summation, and that summation is itself, it has an argument which is the weight vector. And here the data are implicit in this. And so we can now, once we have our residual, what we'll do is we'll say what we want to do is we want to minimize the square of the residual error. So our objective function would be, we can write that as a function of the weight vector, and we're anticipating a differentiation, so let's put in a factor of 1/2. So we'll say that's 1/2, and then we would take that residual error that has an argument that is the augmented weight vector, and we'll square that. Now we want to use a method of steepest descent. So steepest descent, let's recall, that needs the gradient 1 form of the function evaluated at any augmented weight vector. So this needs the, we'll use the chain rule. Let's start writing down the terms that we need. We need the partial derivative of the objective with respect to, well, it takes in a residual. And so the partial derivative of the weight vector with respect to r is, that is, we have 1/2 of r squared, so its derivative is 2/2 times r, so that is simply r. And I'll omit, for now, I'll omit the arguments so that we can clearly see what we have here. The derivative of the residual with respect to the objective is, we would take this and differentiate with respect to phi, so that will drop out and that will simply be -1. The derivative of the activation function with respect to its scalar argument is, we're simply writing that as c, and we would actually have to fill in this for the sigmoid or for the ReLU or for whatever activation function we're using. And then the derivative of the scalar with respect to the weight vector is, well, u equals x1 form times w, and we know from our earlier sessions that the derivative of the product is simply the 1 form, so that is simply the data 1 form, which is the data vector transposed, and we have a 1 appended to it. So now we can write the gradient of our objective. And that means that the gradient 1 form of the objective with respect to the scalar argument is, and now we apply the chain rule, and so that'll be the derivative of f with respect to the residual, derivative of the residual with respect to the activation function, derivative of the activation function with respect to the sum derivative of the sum with respect to the weight vector. And that equals derivative of f is r. Derivative of r is minus 1, so we can abbreviate that as minus r. Now let's add in that weight vector so it's really clear. Derivative of the activation function, we're writing that as the function c. And then we multiply by the one form. And let's just check our units here. R is a scalar value. C returns a scalar value. So it's minus a scalar times a one form is a one form, and that's correct. So the steepest descent direction, D, we know that is minus the transpose of the gradient. And that equals, these minuses will cancel out. This is a scalar, so we keep it. This is a scalar, so we keep it. And this we transform, we simply transpose that. So that is our augmented data vector transposed. And we could also write that, if we need to, as the residual times the activation times the data vector with a 1 appended to it. And this is our convention for creating the design matrix. So the steepest descent is now, so the descent is, we'll say our k plus 1 estimate of the weight vector that classifies the data is wk. And what we'll do is we have been writing S first step, and in artificial neural networks it's more common to see the Greek letter eta. So we'll use their notation. Oh, let's say that is so that'll be the descent, and now that is at iteration k. For the sigmoidal, so let's say, example, let's suppose we use the sigmoidal activation function from previous session, and that would be, the iteration would be our k plus 1 estimate of the augmented weight vector is our kth estimate of the augmented weight vector plus the learning rate, which is what they call the step size, times y, the label, minus the activation function, because that's what the residual is, times the derivative, and that was the activation function for the sigmoid times 1 minus the activation function for the sigmoid, times we take our data one form and we transpose it so that it turns from a one form into a vector, and then we're adding a vector to a vector. And that is the steepest descent algorithm for a single artificial neuron with a single data vector.